Hello, good afternoon. Are we waiting for someone?
Hello, good afternoon. Good afternoon, everyone.
Yeah, good afternoon.
Yeah, you can hear me. Today is the joint seminar, and we shall be starting right now. Is the first presenter ready?
The first presenter is William, and then followed by Alvin.
Okay, William, are you ready to start your presentation?
Yes, I'm ready.
Okay, you may start now.
Okay, can you all see my slide?
Yes, yes.
Okay, so good afternoon. Today I'm going to present this paper with a title of Prediction of Tuberculosis Patient Treatment Outcome Using Multinomial Knife-Based Algorithm and Class Imbalance Data. This paper is done by me and also Dr. Ang, Dr. Lim, Dr. Arvinder from Hospital Sultana Bahia, and also Dr. Yap. And this paper I also presented on IEEE IAS Global Conference of Emerging Technology in 2023 at the May with the paper ID of 298. And now we can also find the paper is published on the IEEE Explore now. And today we are going through the introduction, problem statement, aims and objective, research flow, data set, and also the data preprocessing step. After that, we will go through the result and also future works. So in the introduction, I'm going to introduce the two main points of this paper, which is the disease, the tuberculosis, and also the machine learning algorithm we use is the knife-based. Tuberculosis is an infectious disease which is spreading through the cough and sneeze. And this disease will mainly attack the patient's lungs and other body parts, and eventually leads to the patient death if left untreated. And in the World Health Assembly of 2014, World Health Organization WHO had launched the End TB strategy, which is a blueprint to aim at eliminating the tuberculosis globally by the year of 2035. Okay, here I would like to highlight that in order for a TB patient to fully cure from TB, the TB patient would need to undergo a long treatment program, which spans for 6 months for normal TB variant, and also 1 year and longer for drug-resistant TB variants. And during this period, the TB patient would need to attend the regular meeting with their doctors and also take the drug assigned by their doctors. However, many patients fail to complete the treatment and eventually discontinue their treatment program due to various reasons like financial and also transportation reasons. And next, I would like to introduce about the knife-based. This is a simple, fast, and powerful machine learning model, and is commonly used in the classification tasks like the text classification and also commonly used in the medical field. And the working principle is the knife-based will based on the Bayesian theorem as shown in the slide. And by using this formula, we can compute the conditional probability between the class and also the feature. By using the conditional probability, we can then determine the most likely class according to the new feature we provided. And here is the illustration of the knife-based model. The key feature of it is that it will assume every feature is conditional independent with each other, which means that each feature has no relationship with each other, and it's easier for us to compute and also calculate it manually. So we can compare the result from our calculation and also the computer. And as I said before, the patient will need to undergo a long treatment program to fully cure from TB. And they tends to give up or discontinue and fail to complete the treatment. Here comes the problem where there is a high cost and expenses for treatment failure, and especially critical in the countries with limited resources. The resources here I mentioned, including the financial resources, human resources, and also the medical resources. And previously, there are many research regarding the application of machine learning model in predicting the TB spreading and also the classification of TB patient. However, there are still limited research in the prediction of TB treatment outcome. Here comes to the aims of this paper. This paper aims to provide a solution to assist the hospital in optimizing their resource allocation. And by the optimization of their resource allocation, they can then improve their TB treatment outcomes. The objective of this paper is to implement a machine learning model to predict the TB treatment outcome, and also to examine the capability of multinomial naive-Bayes model in predicting the treatment outcome, to examine the effect of SMRT technique. This is a technique to oversampling the minority class, which I will discuss later. And also to optimize the implement model by experiment different settings of SMRT and multinomial naive-Bayes model. The research flow for this paper, including the collect and import of dataset, the analysis and preprocessing of dataset, and after that, the model will be trained and evaluated. Once the model is achieve the target accuracy of 85% and above, the model will then be implemented. And here I would like to discuss about the dataset I use in this paper. The paper used a patient-level TB dataset is collected from Brazilian Information System for Notifiable Disease, SINA, and all the patient data are collected between January 2001 and April 2021. Inside this dataset, there are around 900,000 records, and all the patient records are labeled either cure for treatment success and die for treatment failure. And as you can see inside the pie chart, there are only 4% of patient is labeled as treatment failure. And this shows an imbalanced characteristic of this data set. So for the data preprocessing step, this paper implemented 3 major data preprocessing steps, including feature selection, where we remove the columns with a larger number of empty value, and also imputation, we remove the records with empty values, and also remove outliers. For the remove outliers, after the data analysis, we found that for numerical column, some of the data tends to clouded at the lower part of the numerical scale. So by remove the outliers sit at the higher part of the numerical scale, we can get a more standard distribution of data. Okay. So this is the SMRT technique. The full name is synthetic minority oversampling technique. This is a technique to generate the minority class to oversampling it, so to increase the signal of the minority class during the training process. And as you can see inside the slide, after the apply the SMRT technique, we can find that the density of purple dot and also green dot, which are the minority class in this data set, had increased, which we can easier to identify the cluster of it. And by apply this technique, we expect to identify the minority class more easier compared to before apply the technique. And here's the experiment of this paper. We had done the comparison between a dummy classifier, which in this case is a 0R classifier, and multinomial naive-Bayes model. We also compare between the normal SMRT and borderline SMRT, which are 2 different implementation of SMRT technique. We also experiment between the different resampling size for both normal SMRT and borderline SMRT. In this case, we use 20, 40, 60, 80, and 100% for each. And for the evaluation metrics, we use the combination of 4 evaluation metrics, which are balance accuracy, precision, recall, and area under our C-curve to inspect the result more in a more complete view. And here's the result. So from the table, we can find that in the PPV, which stands for positive precision column, and also TPR, true positive rate column. After apply the SMRT technique, they are slightly degrade in identify the majority class, which we can solve from PPV and TPR column. And there's a greater improvement in identify the minority class, which we can find from the TNR column. And in here, our minority column, as I said before, is the die patient which has a treatment failure. By combine all of this, we can get a higher balance accuracy and also the area under our C-curve. where we can solve from the BA column and also ROC column. And the best perform model from here we can find that is the multinomial naive-Bayes model with 100% resampling size for the light SMRT. So for conclusion, in this paper, we proved that the multinomial naive-Bayes model and the combination of borderline SMRT technique is capable to predict the treatment outcome of TB patient. And for the next step, we're going to be expanding the research to the whole Malaysia. And we are going to obtain a better data set with local hospital, which is more suitable for Malaysia cultural context. And we are going to implement the proper system after that. That's all from me. Thank you.
Okay, thank you, William. Is there any questions or comment for William from the floor? Okay, if there's no comment or questions, then we proceed to the second presenter, who is Alvin Khoo, on performance of Bayesian network classification models for tuberculosis patient outcome prediction with imbalanced data set. Alvin, are you ready?
Yeah, I'm going to share my screen.
Yes, please.
Can you all see my screen?
Yes, yes. Please
That's right.
proceed.
Okay. So I begin now. Good afternoon, everyone. This is my paper, Performance of Bayesian Network Classification Models for Tuberculosis Patient Outcome Prediction with Imbalanced Dataset. This paper was presented in conference ICA-CIS 2023, and the conference was scheduled on June 16 to 17, 2023. It is a virtual conference. I'm the first author of the group. First, this is the content we will go through together, which is introduction, problem statement, aims and objective research flow, dataset, data pre-processing result, and also the conclusion and future work. Next is the introduction. As everyone has aware, tuberculosis has been a global healthcare concern as we are unable to eliminate this disease. And also WHO also have a strategy aims to end TB in 2030. This paper is trying to end TB in an effective way strategy as artificial intelligence and machine learning has gained attention in healthcare. And it also some evidence shows that it is improved treatment outcomes and it also addresses the challenges with disease. Next is the problem statement. The problem statement is the limited research in TB treatment outcome prediction. And for tuberculosis, we are unable to identify the potential patient that might escape from treatment. And it is also some limited resource in certain countries. And next is the aims. This paper aims to assist in reducing the tuberculosis cases in a sufficient way by using artificial intelligence or also machine learning. Second is to improve the treatment outcome and also to predict the potential cases. As mentioned just now, we are unable to identify the potential patient that might escape from the treatment. So this is why the tuberculosis is still existing, as certain patients, they tend to escape the treatment. And next is the objective. First is to classify TB patient into group using machine learning algorithm. Second is to improve the treatment outcome and predict the potential cases using Bayesian network. Thirdly is to examine the effect of class balances. I will discuss this in the next following. And lastly is to research and optimize the learning algorithm. After objective, this is the overall research flow. Firstly, we will import the data set, and secondly is to pre-process the data set. And in this case, we will select the learning algorithm by using a different algorithm to observe the different result. And after that, we will apply class parameters and train the model, and then we will tabulate and compare the result with using class parameters and without using class parameters. Next is the data set. As you can see, the class distribution, which is the follow-up is up to 98% and the no follow-up is up to 1.7%. This is where the class balances is playing a part as we try to address the problem with class balances, and this is the data set is class imbalance, which might cause the AI might misclassify the patient group. And this dataset is retrieved from a study in South Africa. It is a dataset that conducted diagnosis tests performed on patients to detect TB and also test drug-resistant TB. And next is the data pre-processing before we conduct the AI training. You remove the redundant attributes. Secondly is to remove outliner where certain rows might have missing or unknown value. And thirdly is to address the class balances to balance the weight between minority and majority. As mentioned just now, the majority class is up to 98%. Class balances can assist in giving the balanced weight by providing us a more accurate result. And next is the algorithm implementation. As I mentioned just now, the learning algorithm. There will be 6 algorithms to be implemented to make comparison for the Bayes network classification model. And the algorithm are Herkheimer, repeated Herkheimer, LAGD, Herkheimer, K2, simulated annealing, and double search. The different learning algorithm will be applied to find the most optimal structure for specific dataset. It can help us to observe that how different algorithms can affect this study case. And as this is a medical dataset to tuberculosis, most of the medical dataset is often lead to imbalanced cases. And next is how we conduct the experiment, run all the algorithm with same model, which is Bayes network, and all the learning algorithm with class balances and without class balances. And we will examine all the metrics to see for the best result. And how do we evaluate the result? By using several metrics, which is confusion metrics, and the most straightforward is the accuracy. And also not only accuracy, several metrics to be observed and studied, which is precision, recalls, accuracy, and NFI score. And most importantly, to tabulate all the results for a better observation, and we can see the effectiveness of each algorithm. And next, this is the result before and after apply the class balances. As you can see, before apply the class balances, the TP rate, which is the true positive rate, is up to 0.97, which is 97%. However, the false positive rate is also up to 57%, which is on the K2 algorithm. You also can see from certain algorithm, the false positive rate also up to 0.98 for the LAGD, and also for simulated annealing is also up to 0.90. After applying the class balances, as you can see that although the true positive rate is 0.89 for all the other learning algorithm, is also showing lower value compared before using the class balances. However, the false positive rate is also lower, much lower. It shows that how class balances is assigning the weight between the majority and minority class. It can also be observed that other value is also have minor changes. And next is the discussion. As these accurate prediction are crucial and critical in machine learning, as the biased model overestimate the majority class. As just now, one of the class is up to 98%, and it also could underestimate the minority class. As this paper has presented that class balances is a very useful technique to addressing the problem of class imbalance by improving the accuracy of modern learning algorithm. And next is the conclusion and future work. This study was originally aimed to using the local data set, but due to some constraint, we are unable to obtain a data set locally in Malaysia. First, we aim to expand the research to nationwide Malaysia. And secondly is to obtain a data set which we can localize these studies and providing a more comprehensive analysis. And thirdly is the most important, try to implement the following proposed system to the medical field. And that's all for me. Thank you.
Okay, thank you, Alvin. Anything from the floor to ask Alvin on the presentation that he has done? Okay, if there's none, let's proceed to Dr. J. Joshua Thomas for the next presentation. Dr. Joshua, please.
Yeah, I'll share the slides. Just a second.
Thank you.
Hey, good afternoon. So the title for today's seminar is Machine Learning Techniques for Predicting Remaining Useful Life of Machinery for Sustainable Manufacturing Lines. I'm Dr. Joshua, and I'm working with Department of Computing, UOW Malaysia, KDU Penang University College. So every day we rely on a wide range of machines. So, but the truth is that every machine eventually breaks down unless it's being maintained, isn't it? So companies follow different maintenance programs to increase operational reliability and reduce the costs. One way is to reduce the maintenance is reactive maintenance, where the machine is used to its limits and repairs are performed only after the machine's failure. So we are in this direction for this research work. There are various types of maintenance. Our focus is on predictive maintenance. So let me just give you a brief on what is reactive, preventive, and predictive. So reactive is, as I mentioned earlier, is about a small light bulb. Okay, it's very easy for you to change the light bulb until it bursts off or it fuse. So that kind of approach is reactive maintenance. Okay. What if it is a complex ones? You consider a wind turbine, and you're going to change its high-speed bearings, and that is an issue here, right? So probably you cannot use reactive maintenance. So reactive maintenance, you just use that as a light bulb. Okay? You just change it. But whereby in your wind turbine like this, you want to change the bearing, probably you may have to do a particular schedule. So when you look at the graph here, so we call this a standard application used by researchers. It's an exponential degradation model that tracks the failure of the high-speed bearing used in the wind turbine. So the condition indicator here is shown is in the blue area. And you can see there is a degradation model that is predicting the bearing will cross the threshold value, approximately probably 9.5 days in this case. So either you change the bearings within 9.5 days, or you can stop the machine for maintenance within that particular duration of time. So that kind of complexity is there. So reactive is more towards on a bulb, but it doesn't apply to a complex systems. But there is another maintenance mechanism available. We call that as preventive maintenance. So what do you mean by preventive is, which is good, but you may need to be a bit conservative in planning of doing this maintenance, probably because you see that there is a cycle or the machine, then you already stop, but there is still an usable condition. The machine is still in usable condition. In that case, you stop it earlier and you are losing the the cost, you're increasing the cost. Probably you don't unused area that you just keep on giving for maintenance. The third component, which is ideally work on this particular work of the research, is predictive maintenance. So the predictive maintenance, the good news here, the maintenance let you estimate the time of failure or the time to failure. It also highlight or pinpoints the problem in your complex machinery, and it helps you to identify which part is to be fixed. Okay. So in this case, if you can see from the 3 overview summary here, so reactive maintenance, you stop the machine because, or I can say that the machine already in failure, then only you are going to change the repairing parts. And it acquires, because we do not know, it's a small bulb is just easily changed. But how about a wind turbine? That is the example I gave you earlier. The second one is the preventive maintenance. You stop it earlier, and it has still have the valid life, and you also incur the cost. The third one is a predominantly, which is very good, and there are also some challenge here. But you try to optimize the time to do the maintenance. So you start, there is an indicator that's now you started observing that the machine, when it's going to be end of the life cycle of the machine, you are observing that. But you can see there is a corner, the corner only you are able to identify. Oh, this is the area that within the 20 days, within 10 days, within 5 days. So you don't lose a lot of money on that particular aspect. So that is one area of research that is contributed here. The second one, we are using that the same concept here rigorously. We may need, if you want to develop a predictive maintenance, obviously you need to invest as long as a development of an algorithm to do a prediction, to predict a time window that going to show you within how many days your machine will fail and when you need to do the maintenance. For example, in this research, we take a data set, it's a aircraft turbo engine data set, and we are applying the predictive maintenance algorithm and try to find the failure in the days, probably 20 days or 10 days and so on. So ideally, the same setting is more suitable, could be an assembly line of equipments in the manufacturing sector, or you focused a particular machine in industry, for industry machinery like CNC machines. So this is one aspect. What do you mean by this remaining useful life? I give an illustration here very quickly. So when you look at the first diagram, you can see the grass cutters here, and the red ones are unused, and the blue ones are in a tip-top condition. You can use it anytime. And the middle one is with a dotted with a yellow one. So it cannot be used, or we do not know when it stops. So even though you have an intelligent preemptive maintained based on these equipments, probably could be have these scenarios, but it doesn't understand. We are not able to measure it. What is the remaining useful life for the particular equipment? The second diagram on your right, it shows RUL for one machine, right, on the top one. So that means there are machines available, and the two machines are ideally, it has a remaining useful life, and you are confident enough to assign it, even though you are using a smart inventory of historical usage based on the equipment or data. Okay, and there is another aspect here when you can see that there is a chainsaw available here. We may not use it because we are going to use for grass cutting. We cannot take that one, right? So ideally, in that case, what if you have to maintain and monitor this in a complex scenario like complex machines? Probably you may need a dashboard. So here we are talking about two things: preventive maintenance and the remaining useful life. So under the predictive maintenance, the predictive maintenance can be done in two ways. Either you do an anomaly detection, or you can do a remaining useful life. So the remaining useful life, it involves try to track the accuracy determined by an object, or it can be like to fail before its current condition or based on its current condition. Okay, but however, unlike the uncertain nature of such predictions, this RUL predictions seeks to provide a scientific evidence is based on either a strong algorithms or it can be estimate the lifespan of the machine. Okay, so that is the main core idea. So in the literature, I can show you here. We take the 1998 until 2022 papers, but we don't take the batch papers, but we consider 2019, 2020, 2021 articles, and you find that these 3 years is of MCOs, right? In majority of the companies. So people are working on fully automated and self-monitored, remaining useful life related, and you want to try to control the machine when you are in front of your laptops. That kind of literature is available now. So probably you can see that in year 2020, it's all Q1 papers, probably this one, 200 over papers on 1 year. And still it's going on, right? I don't have that on another data here, but you can see that from the reference list here. But when you look at the 4 or 5 references, the core references, which is more useful, you can see that smart manufacturing related articles and probably a convolutional neural network, or when they use to identify the sensor devices, not only machine learning methods, they can go in depth on deep learning or the hybrid methods. But roughly, you can see these 3 years, people are working towards this direction, remaining useful life of a machinery or equipment or a device and so on. So on your right-hand side, there's a list of data sets. And I just want to highlight the one that is used here. And most of the researchers, 28.45% of researchers probably, they use this NASA's CMA PSS dataset, which is a aircraft turbo engine. So the reason is they are working on this. It comes with a multiple sensors, and it's a huge amount of data produced from the dataset. And so we take that data sets and we go further down on the research. So we have a pipeline. We have acquired the data from the data set, and we do have a pre-processing stages. So the pre-processing stages, it's from the benchmark data set. We just actually, it comes with 4 different larger data sets, but we take one data set which has 100 different types of turbo engine fans, and each fan must have at least 21 sensors attached to that. Okay, we'll come back to that. But during the pre-processing, there's another method we are also available, but could be a future one. You can simulate and try to create a synthetic data, and you mix with the original data set, and you can apply the techniques and so on. So the main contribution of this particular work is on machine learning algorithm. We don't want to work more on cleaning those data sets, okay? But that's the reason we just go for the researchers' highly contributed data set. The third component is identify the conditional indicators. So if we consider a machine, it could be working fine with a healthy operation. Then after a certain period of time, it reduces its fault tolerances comes here. And also in this case, we consider from the data, from the given data set, we extract features by using extracting the features from the data set. Then we feed into your machine learning model, and you have a combination of machine learning model together with decision trees, a gradient booster with decision tree models, okay? So that we are able to estimate the machine's health in a remaining useful life in a various components. You can see that you are able to slowly monitor it with a period of time, because it's over the period of time only the machine will halt. So you are able to analyze when it could be a 10 days is fine. It's a 20 days or no. Is it a 5 days? You are able to change the parts. Then you can stop within the 5 days. Okay. So that much of detail we are able to generate when you get these results by using this mechanism. Okay. And in literature, we have the random forest selection of approach tried to prove as one of the ensemble methods. But in our research, in this paper, probably we use this another type of ensemble method. We combined with the gradient booster regression with to predict the model, to combine with your decision trees. Okay, so first you can see the first equation. The first equation is an algorithm to create a base model to predict the data. So here the predicted value of the base model is the average of the dependent variable. Okay, so the idea here is we try to start with an average model, And purely then we move on to the equation can be adapted to the gradient descendant, gradient booster algorithms. Okay, so that's the first equation. So here, the L represents the loss function and the gamma is the predicted value. So the goal of this equation is to find the gamma value where is the loss function is minimum. So in this research, the dependent variable is a continuous variable. Thus, the loss function in equation has its meaning here. Okay, so here another equation in your equation number 3, y suffix I is a dependent variable and gamma suffix I is a predicted value. And as I mentioned earlier, that the dependent variable in the research of the gamma value is a continuous type. So the next stage of to calculate the pseudo residual values. Of course, we take the benchmark data set, but it does has its residual values. We do consider the residual values, but the equation says we use the pseudo residual is equation to the dependent variable minus the predicted values. So that is the equation number 4. And you can see from here, capital F X suffix S is a prediction model. Already we trained. Then M is the number of decision trees we added. So here is another combination here. So during the training process, we created a decision tree. Then we assign the decision tree, train the model. We don't literally train again all the whole data set. We identify the residuals. From the residual, we minus the predicted value. Then we can apply a decision tree model to train again. So to split the data values, then you are going to do the final prediction. So that is the contribution of the machine learning model. We call this an ensemble model here. We do have a PCA, principal component analysis, and we don't use it directly here, but we use it to contain the training process, try to minimize the data set so that it can be speed up the training process. In that perspective, we can use it. I can show you that in the subsequent slides. So I want to show you the dashboard that we have come up with this. Try to understand the dashboard. A little illustration here. Then I show you a very quick demo in the end of the session. So you can see there is a turbofan 1 is selected. And the turbofan has the maximum cycle of each fan is 200 cycles. So here in this particular turbofan is 31 cycle is run. It's in the 31st cycle, and there are 3 different operations. So probably operation 1 in green, and another one is in a blue, another one is in red. And the remaining useful life for this particular turbofan, you can see all the 21 sensors will be displayed. If we have this machine learning model, we train across to that and analyze that. For turbofan 1, it has run with the 31 cycle, and this still remaining 113 cycles left. Okay, so this is this kind of dashboard that we have created. Okay? And this is the simulator. I just quickly illustrate. So we do take the first EDA data analysis for the NASA's turbofan engine. It's a degradation simulation data set. And if you look at the data set features here, there are 4 data sets in a complexity here. So the engine operates normally in the beginning, but it develops a fault over the time. So that is the situation in the data set here. So initially it works well because it's a new engine, and in a period of time it to a failure. Okay, so for example, while the test set we used a time series end of the failure, so that we are able to capture the remaining useful life. So training set, we run the whole system. Then when the machine is running, we take the training set. But the test set, probably we take the time-based end level of the particular machine. That could be so that our goal is to predict the remaining useful life. So the parameters inside the data set is about engine unit number, time in cycles, 3 operational settings, and 21 sensor rating. Okay, that's why you can see the 21 sensor rating if you select any one of the machines here. Okay. Okay, so based on we take our data set, we just take the first data set, FD001 out of 4, because it comes with a reasonable amount of data, and it comes with 46 cycles, is quite large in this case. And it shows here some descriptive statistics of the operational settings. So we take only one operational setting for this case. We have a turbofan size of this data set. We have 100 turbofans. with each turbofans comes with 21 sensors attached to that. And we can also see from the RUL histogram. So the histogram has reconfirmed that the descriptive statistics of the engine cycle above where the most of the failures occurs. So in this case, for experimental data set here, as from the many researchers using this experimental setting, everyone uses a similar type of data set is 200 cycles. So 200 cycle, it works fine. After that, it goes a failure model or its end of life of this particular mission. So even though it has a 300 cycles, okay. So even though the descriptive statistics shown here, we try to look at the patterns before we extract the features. So here there are two types of development techniques. So probably model-based, mathematically model-based or data-driven. Our adoption here is more on data-driven model. So here there are a number of sensors for you to analyze, to have a look. We just take graph number 1 is a sum of the sensors like sensor 1, 5, 10, 16, 18. So they are showing one single line on x-axis. We don't able to capture any fluctuation here. But whereby in sensor 2, you can see there is a trend of fluctuation going up. And you can see from the sensor 6, all from the downward fall of the data sets. So again, the sensor 6 and sensor 1, that means out of 21, you have to find this type of patterns already. Okay, for 100 fans also, you are able to find this type of patterns. This will help you to go and analyze an extraction of feature selection. Let's see one glimpse of it. Let's say I put one particular machine, for example, turbofan 1, and it has 21 sensors attached to that. And what is the RUL distribution histograms? So the histogram also, again, it can see that so 200 cycle is works fine. After that, it's shrinking down. Okay. So we are extracting the features. It's not a confusion matrix. This is an extraction features diagram with a heat map. Just to show you here, the positive value is blue indicators. That is a positive relationship between two features, while the negative value in red indicates the negative relationship between the sensors. Let's say sensor 1, 5, 10, 16, 18, and 19 has a 0 related remaining useful indicators. There is no relationship between them, right? So we cannot simply run the experiments. We just try to extract the features, try to identify the patterns, then you can collect that particular sensor values, feed into your machine learning model. Okay, then you can see you're not running and explicitly wasting your hardware or computational speed. So here I show you another diagram. Here is the principal component analysis. So the graph shows that we take only 10 components, at least requiring a 90% percentage of information. That's a 21 turbofan of hundreds. You have 26 or 21 sensors attached to that. And what is the extraction? At least you can take a portion of 10 components, and which can at least very, very useful information for the machine learning to predict that. So that case, we use the principal component analysis. So you can find that in literature, people use PCA attached together with another type of machine learning techniques. But in our case, we just use only to speed up the computational speed and also try to control the size of the data set. We use the principal component analysis. Okay. Here goes your training and testing side. So you can see there are two life cycles here. Again, training of the left cases. So you look at the ID1, cycle 1. So the maximum reuse RUL is 191 and until 187. So that is a training side. And for the test side, the machine is going to die, for example, if going to end the life of the machine. So we're going for 142, 141 until 138 in this case. So that is the selection of data that we use from the given 100 fans or times your 21 sensor readings here. Okay. The result shows here. We also do average model, then we apply linear regression, we apply improved linear regression parameters, then polynomial regression, support vector emissions. But when we are able to achieve the combination of gradient boost with decision trees as a combination of extraction of random forest, we are able to achieve 0.82. Actually, we achieve 0.83. I'll show you a quick demo here. Just a second. I just change the screen here. Okay, so here, this is the system. This is the proto model here. And we load the data sets and we use SQL Server to do that. It's a huge amount of files, so we need to use it. We load it again, and it will create the row. It run it first, then before we go for the dashboard, it links with the dashboard together with your Python models, which we pre-created. The model pre-models will be connected back here. Okay, I'll quickly move on this. Sorry for the over time here. Okay, so there's a link here. I would like to show you that. Okay, it'll run the experiment here. You can see the dashboard. So here goes your engines. So here, the one I sample screenshot. So you can see that we have 100 turbofans. Probably each one has a 21 sensors attached to that, and we just use only one setting. Okay. Okay, this is another machine we just randomly I'm choosing here. Okay, this is a 28th machine. Then you have a lock feature. It's a very simple one. We do have this voice enabled approach. So instead of imagine you have a huge amount of turbofans, you just call by name and something like that. So here you can see that we use a gradient booster regression. We are able to get 0.83. You can see the other. Yeah, you see that we have tested with other. We start with the baseline model, the linear regression. Then we have a polynomial linear regression approaches, support vector missions. Then we have the combination of the hybrid methods. Okay, so you can see that support vector mission, we are able to get only 0.8 as a R2 value RMSE. I think. Yeah, this will show them the voice features. So I just skip that. Okay, I think that's all from my presentation. You have questions, so it's published actually. If you have any questions, please ask me. I try to answer.
Any questions or comment for Dr. Joshua?
Okay, please, if you have any questions, we are writing some grants based on this. Please do in touch. I will try to help you we can share knowledge. Okay, thank you very much.
Okay, thank you, Dr. Joshua. Coming next will be from Bach, Department of Computing, for his presentation. Bach, are you ready?
Yes.
Bach, are you presenting right now? We cannot hear you.
Can you hear me?
Very soft. Can you turn louder?
Can you hear better now?
Still soft. We cannot see your presentation also, your slides.
Oh, no, I'm editing the. Can you see my screen now?
Yeah, screen is on. Can you speak louder? It's a bit soft.
Okay. Speak louder. Good afternoon, everyone. My name is Huân Xuân Bách. Today I will present my work with the special feature enhancement on facial landmark. So my presentation will follow this structure. Firstly, I will provide a brief introduction followed by the methods and dataset that I use in my study. Next, I introduce my robot methods. Finally, I will share the result that I achieved. The introduction in today's digital society, image processing plays important roles. Each technique like image enhancement improve visualization and find a wide application ranging from mobile apps, desktop software to websites. Moreover, these techniques contribute significantly to the biometric security, advancing area like fingerprint, iris, object recognition, and face recognition. So, in my research, I utilize the YouTube face dataset. This extensive dataset contains around 1,600 subjects from over 3,000 videos, offering benchmark for facial detection or recognition. The data set includes approximately 2.5 billion images. Many images of the data set in challenging conditions like poor lightning, various facial position, and blurriness. Follow that, I also use 3 color space in my methods. First one is RGB, BGR, and YUV. Each color space has its own characteristics and advantage. RGB and BGR are addictive color models, and YUV is particularly useful for the human visual perception. My aim was to leverage the strengths of these color space for image enhancement. When we work with the digital image, so a common challenge is the noise and low quality images. This can be due to several reasons, including the limitation of an image acquisition device, environmental factors, and the physical nature of the system. To tackle this, I employ various low pass filter like median filter, Gaussian filter, and the bilateral filter, as you can see from the slides. And the next one is the high pass filter. Specifically here, I use Laplacian filter to enhance the edge in the image. If this filter calculates the second derivative of an image, helping to determine if a change in a junction visual value in from an edge or the continuous direction. And after apply on the color space or filter, I will use the delift for face detection and apply 68 landmark points to identify the significant facial features. The process involves 2 steps. The first one is face detection in an image. The second one is detect the primary facial structures on the region of the interest. And here is my robust methods. Numerous of low pass and high pass filters, as well as contrast sketching techniques are applied to the original image to achieve a better result for face detection. So you can see in the figure 5, show the flow diagram of the Roboso facial feature enhancement for face detection. The original image comes from the YTF database. In addition, the conversion of images from either RGB to YUV or RGB to BGR images undergo contrast stretching prior to being subjected to further processing. After a low pass or high pass filter is applied to improve the image qualities. I propose 6 different methods, each involve different combination of color space conversion and contrast stretching and filters. One common step in many these methods is to convert the image from RGB to YUV color space, then equalize the white channel. From there, method 1 will convert the image back to the RGB color space. Method 2 will apply the bilateral filter to the image. Method 3 is apply Gaussian filter to the image. Method 4 apply the median filter. Method 5 is convert the image back to the RGB color space and apply the Laplacian filter. Method 6 a bit different from the other. If I convert to BCR color space, then apply the Laplacian on it. So each of these methods can produce a different results. So to validate my approach, I use mean square error MSE in a short form and big signal to noise ratio BSNR in the short form to measure the quality of the filter images. MSE measures the peak error and the BSNR measure the cumulative square error between the filter and the original RGB images. A lower MSE and a higher BSNR indicate a better visual quality of the image. So here you can see the results. I compute the MSE and BSNR for each image in the YTF database and take the average of all the images as shown in the figure 6. Accuracy is obtained by computing the number of the hit face over the total number of the images with the face. As you can see here, the MSE of the method 1 and 3 is the highest one. With the lowest value when compared to the other methods. Additionally, the BSNR values for method 1 and 3 also is the highest values. So from there, we can observe that method 1 and 3 can achieve the better visualization for the human perception. So here is the result for the accuracy. Figure 7 presents the accuracy result of the methods compared to the original image. And you can see that method 1 and 3 achieve the highest accuracy rate, which is 95.12% and 95.07% respectively. So that's all of my robot methods. Thank you for your attention.
Okay, thank you, Buck. Any comments or questions for Buck regarding his presentation? All right, if there's none, can I have the last presenter, Mr. Saravanan Raman, for the topics assessing the relationship between service traits of and service dimensions and the mediating effect of service priorities and shared services. So, Sarah, can I have your presentation, please? Okay, just give him a while. He'll be joining, presenting in a while.
Okay, everyone, can you hear me?
Yes, yes, we can hear you.
Sorry guys, I'm actually in a class. So let me to present my part here. Okay. Okay, this is about assessing the relationship between service trade-off and a service dimension and the mediating effect of service priorities and shared services. This paper was recently presented in Marketing Conference 2023 at the University of Birmingham. So let me to explain to you the purpose so on. Okay, the purpose of this research is to measure the effect of service trade-offs and a service dimension on a service employees. The mediating role of the service priorities and shared services are measured in this model to find out whether they foster relationship or not. Dealing with a trade-off during the decision making, particularly in a diverse service scenarios, is a challenging proposition for service firms. Okay? This is a particularly when the service organization struggling to attain an optimal balance between efficiency and also cost reduction. Okay? So essentially, the trade-off is in an industry wide term used to describe operational compromises made by the managers and also the service employees in a daily manufacturing and production activities, as mentioned by our Rosenvik in 2010, and it was supported by Samito and Gianodis in 2017. Due to the key differences in the activities conducted in the manufacturing and services sectors, okay, there is a distinct variance in how trade-off decisions are affected in a manufacturing and a service organization. And today, when you look into the customer expectation and the service sector have grown increasingly demanding, particularly in light of the concerned technological advancement and the need for customized services to match customer specific needs and reduce the customer related service failures. So to match the customer needs and reduce the customer induced service failures, okay, service employees constantly struggle to strike the right balance between maintaining an uninterrupted flow of service while simultaneously matching customer needs in the service delivery process. Okay. It's about background. Okay. So the main goal, the main objective is to review the existing literature in the field of service marketing and establish the new service trade-off model, and then to identify the potential root cause of the service trade-off and practices and frame the service dimension that cause a service trade-offs. These are the research gaps. So the research attempting to present the evidence and argument against the Skinner's model. Skinner's introduced trade-offs in the manufacturing in 1969. Okay. And then the second gap is about empirical gap. Okay. Very little research has been done to know under which circumstances trade-off occur in the service operations. Okay. And then the third gap is about a methodological gap. Okay. Very few framework exists in a service operation literature that connect the operation concern with a marketing concept. And fourth gap is a population gap. So most of the trade-off research was conducted in developed countries like Netherlands, US, even Germany, and so on. So I believe that by undertaking this research, you will at least can contribute something to the developing countries from the developing countries perspective like Malaysia. And then the last gap is the evidence gap. Okay? Service, we must understand that, okay, previously very well-known variables that they use to explain about a service failures, service improvement, service expectation, perceived service. Okay, we always refer to the service quality introduced by Parasuraman, Sethamal, and Baring in 1985. Till today, okay, the sub-call model is actually used widely in the service industries, okay, to understand about the expectation and perceived services, okay, the gap between the expectation and perceived services. But mine, I'm looking into what the root cause, how to analyze the root cause in the service industry, especially in a service firm, service organization. So what I did is I tried to find the right service dimensions without looking at the like a generic model like a sub-call model that widely used and widely accepted, one of the very reliable model. So in my context, I try to use all the new variables based on a Skinner. I also have some variables from Skinner's model, and then I introduce some of the few more model variables into my model to make sure the model is a complete model, and then use a mediator to test, to assess the relationship between a service dimension and a trade-off. So these are the variables that I use. So service capacity and demand, serviceability, service process, service flexibility, service design. These are the 5 service dimension variables, and service priorities and shared services are the mediators that I use. And then you can see that another one is my user service trade-off. So these are my conceptual framework. I can see that service capacity and demand, service design, serviceability, service flexibility, service process, service priority, shared services, and lead to the service trade-off. So I use what we call G power to determine the sampling size. 350 responses was collected from 400 questionnaire which was distributed. And then now we are looking into the result analysis. For information, guys, okay, we use PLS SEM approach to study to determine the what we call it the parameters, and then like a few critical decisions lead to our decision to use a PLS SEM. Firstly, this study exploratory in nature, where the research objective is to explore the key factors influencing service trade-off related to the efforts, effort from the service employees in Malaysia. And then we use the assessment of measurement model. 3 main assessment criteria are used to measure the goodness of measurement. Okay, these 3 assessments are internal consistency, reliability, convergent validity, and discriminant validity. Okay, the internal consistency of reliability is measured using a composite reliability. So to indicate adequate internal consistency, the composite reliability value should be higher than 0.7. That's why you can see that okay, we actually drop those items in a question that below 0.7, like priority 1, service capacity and demand 2, service capacity demand 3, service capacity demand 5, service design 1, service design 2, service flexibility 1, service priorities 1, service priority 2, service priority 10, service priority 11, service priority 12, service priority 13, and trade-off 8. So you can see these are the items that we drop from the questionnaire because their loadings are below 0.7 as mentioned by in 2011. So this is for HTMT analysis. Okay, so from here you can see the reading less than 0.9. Okay, with a confidence interval containing or exceeding 1.1. So the discriminant validity was adequate. Next, we are looking at the assessment of the mediating effect. Okay, this study actually adapted from the Pritchard and Hayes 2008 method, okay, of bootstrapping to look at the indirect effect of to assess the mediating effect. So from our from our research here, we can see that Pritchard and Hayes stated that the established mediating effect, the indirect effect must be significant and 95% of a good confidence interval, okay, CI, should not straddle in 0 in between indicate there is a mediation in. Okay, so the bootstrapping analysis result, okay, you can see that show that our 4 indirect effect, okay, where the beta equal to 0.083, and second you can see from here the beta here, okay, we have the hypothesis 1 here. Okay, hypothesis 1, service capacity and demand to service priorities, okay, to service trade-off 0.083. That's why we say that this is a mediator, service mediator. There's no direct, you can see from service capacity and demand to the service through the service priorities, we go to the service trade-off. Second one, hypothesis 2, you can see that, okay, the beta value here 0.288, okay, and then supported, okay, all supported, supported. And service design through the service priorities, service trade-off, okay, is actually you can see that, okay, we are not, this the hypothesis is actually rejected because they're not supported. And then you can see the service design to share services also not supported, okay. And hypothesis 5 about a service process to share services, okay, is 0.07, okay, is supported, and service flexibility 0.213 is supported. So you can see that okay, the p-value is more than 0.01, okay, and then the bias corrected with a upper level and a lower level. Okay, that is all about my part, okay, for this presentation.
Thank you, Sarah. From the floor, any questions or comment for Saravanan?
Thank you, Saravanan, for the wonderful presentation. Just want to ask you, where do you apply this service industry so that everyone can understand? We understand that your results are promising.
Oh, really? Okay. This actually I apply this from data. Can you see this?
No, the application of your research.
In a higher education sector.
Okay.
Any other questions from the floor? Okay, so if none, that's all for today's presentation. Thank you all for attending, and thank you for the presentation. Bye-bye, everyone.
Thank you.
Thank you.